Gay-Lussac's law defines the relationship between the pressure and the temperature of a gas. According to the law, when volume is held constant, the pressure of an ideal gas is directly proportional to its temperature.
One practical example of Gay-Lussac's law is how tire pressure increases with temperature. As the temperature gets warmer, the pressure inside the tire also increases.
Keep watching for an experiment about Gay-Lussac's law. In this experiment, the constant volume represents the glass because its volume is kept constant. Let's see how the temperature will affect the pressure in real-life application.
Here are the materials we used for the experiment: glass, candle, food coloring,
Plate.
and a lighter.
So what we're gonna do first is fill the plate with water. Then add some food coloring. The next step of the experiment is get your candle, place them in the middle of the water, and light them with lighter.
For the last step, take your glass and place it over the top of the candle.
After a little while having our glass over our candle, you'll notice that the candle flames will get smaller and smaller until it's extinguished. If you watch closely, you'll see that the water level underneath the glass begins to rise as the candle fades away. The water level will continue to rise for a short time after the candle has been fully extinguished.
Here are some sample problems about Gay-Lussac's law. Problem number 1. A 30-liter sample of nitrogen inside a rigid metal container at 20 degrees Celsius is placed inside an oven whose temperature is 50 degrees Celsius. The pressure inside the container at 20 degrees Celsius was at 3 atmospheric pressure. What is the pressure of the nitrogen after its temperature is increased to 50 degrees Celsius? So the given in this problem are as follows. Initial temperature, which is 20 degrees Celsius, which we will be converting into Kelvin. So 20 degrees Celsius plus 273 K is 293 K. or 293 Kelvin. The initial pressure, which is 3 atmospheric pressure. The final temperature, 50 degrees Celsius, which we will be converting into Kelvin also. So 50 degrees Celsius plus 273 K is 323 K or 323 Kelvin. And final pressure being unknown. Notice that the final pressure was not stated, thus being the variable which we will be looking for. Now let's get into the computations. First, to not confuse you at all, write the formula of Gay-Lussac's law first. So it is P1 over T1 is equal to P2 over T2. Then isolate P2 to one side. So it will be P2 is equal to P1 times T2 over T1. Then, substitute the variables with their corresponding given values. So it will be P2 is equal to 3 atmospheric pressure times 323 Kelvin over 293 Kelvin. Then solve by multiplying your numerators, 3 atmospheric pressure and 323 Kelvin before dividing it to 293 Kelvin, and your final pressure or P2 should result to 3.31 atmospheric pressure. Here is another problem for you. Problem number 2. Determine the pressure change when a constant volume of a gas at 1 atmospheric pressure is heated from 20 degrees Celsius to 30 degrees Celsius. So the given are initial temperature or T1 at 20 degrees Celsius, which will be converted to Kelvin, so it will be 293 Kelvin. P1 at 1 atmospheric pressure, and the final temperature or T2 at 30 degrees Celsius, which will be converted to Kelvin also, so it will be 303 Kelvin. So don't forget to convert your temperature from Celsius to Kelvin when necessary. And of course, the final pressure or P2 being unknown. Notice that the final pressure or P2 was also not stated in this problem. Thus, we pattern our computation from the first one. So we should write the formula first. P1 over T1 is equal to P2 over T2. then isolate P2 to one side. The formula will be P2 is equal to P1 times T2 over T1. Then substitute the values. P2 is equal to 1 atmospheric pressure times 303 Kelvin over 293 Kelvin. Solve by multiplying your numerators 1 atmospheric pressure and 303 Kelvin before dividing it to your initial temperature, thus resulting to 1.03 atmospheric pressure, which is your final pressure.
Thank you for listening, and we hope you learned from us today.